Well, thanks the organizers, Cyprian, Camille, and Maria for putting together this amazing school. Also to John, that will come today or tomorrow, and Danny. I know that they have been working a lot to make possible that all of us we are here. It's also very difficult to talk after Danny. He put the level very, very high. His standards are very high. I will do my best. In my favor, I have to say that Danny and I, in the last weeks, we have spoken a lot about how to coordinate properly our talks in a way that we do not overlap and that they are complementary each other. So, as you see by the title, because the title is Solute Mixing and Chemical Reaction in Unsaturated and Multiphase Flow. And just to let it clear, unsaturated, for now on, is when we don't move the immiscible phase. For example, it can be air in the soil. And multiphase flow, it will be when we move all the phases except the solid one, or with the exception of the solid one, when we move, for example, water and air in the porous medium. So, I agree with you, Danny, this doesn't work very well. So this will be the outline that I'm going to follow, and this is what I call a kind of a Lego presentation, because it's divided in blocks, 4 blocks, and who knows if we will be able to do the 4th. I'm pretty sure that we can do the first 1 and 2, first, second, and third. So, as I mentioned, we're going to start with the unsaturated flow. We don't move the immiscible phase, and we're first going to discuss about mixing, liquid-liquid reaction, but also liquid-solid reactions, in this case, absorption. And for the multiphase flow case, when we move everything that is there, mixing, liquid-liquid reactions, and also liquid-solid reactions. I would love to show you this, because this last section or block is where I would like to show you what that Danny didn't have time, which are what are the implications at large scale. So let's hope that I don't consume all my time. So, what is the motivation of this lecture? The motivation is the fact that basically the unsaturated zone that was introduced previously by Danny is a bioreactor in which we have fluids that they are moving, we have chemicals that are transported, we have microbial activity that is taking place there. Okay, we can have here how heterogeneous can be the fluid velocity and the chemistry in the soil. We can have sources of nutrients like organic carbon, but we can have also a contaminant or a nutrient that is transported. And of course, this is in interplay continuously with the microbial behavior, with the roots, with the fungi, with the microbiology. So I adopted this slogan from Danny since many years ago, that soil and vadose zone are fragmented aqueous habitats. So this is one of the main motivations, but it's not the only one. Something that I'm going to do in the presentation, and just to let it clear, the slides that they have this kind of brownish background are the slides in which I'm going to use for first time certain concepts. For many of you, probably they are very basic and it's come on, Joaquin, this is, but probably not for everyone. So there are a few slides all over the presentation in which I would like to let clear certain concepts that no one is lost. The first one is that you're going to see in many of the slides this couple of dimensionless number, Peclet, that relate the diffusion time versus the advective time. And also the Dunn color in the case of the reactions, okay, the ones that relate the advective time versus the reactive time. If we have Dunn color that are much bigger than 1, it means that we have very quick reaction, and then mixing is the main driven of the reaction. And if we have Dunn color smaller than 1, then we have what we call kinetically driven reactions. Usually are the reactions that are very slow. Okay? Clear that, because
Can I make a quick comment here?
Yes, you introduced that yesterday probably.
No, I didn't talk about down color, just to say, just in case for the next lecture, some people do it with diffusion instead of advection. Of course, they are more or less interchangeable.
Yeah.
I like the diffusion one. So,
I use both.
But they're both fine.
I use both, yeah.
You can change from one to the other by multiplying by Peclet.
Yeah.
Just putting it up.
Can you show us what it is that he's talking about?
Yeah,
no, it's
definition.
If I go to the definition, Dunn color number can be defined here with the diffusive time instead with the advective time. And yeah, I mean, there are two done color numbers, the affective one and the diffusive time. Actually, I use both, and later in my slide, I use a done color that actually is diffusive.
I'm just mentioning it so
Yeah.
people who are not used to it.
Yeah. So I should add here, or make the,
They're both fine.
yeah. So one more definition, and then after we go in deep into the topic. You will see all over the presentation this symbol, theta. Danny already introduced about that. Danny has used this for contact angle, but in this case, is widely used in the soil physics community for water content, the volume of water versus the volume of soil. And a normalization of the water content is what we call saturation degree, when we divide the water content by the porosity or by the saturated water content. Okay, because you will see this SW all over the presentation. Back to the motivation. And the motivation comes from the previous presentation. How has been traditionally solved the unsaturated flow? Okay, or the movement of the water in soils in the unsaturated zone. And then for that, we have, of course, to start always with the conservation law, in this case, or volume or mass, as you prefer. Okay, the variation of water content with time plus the flux. And we saw before that Buckingham did a huge contribution in the field, and then basically demonstrate empirically how we can define the flux. And then we have here the unsaturated hydraulic conductivity, and we have also here the matrix potential, introduced before by Danny. These two are very non-linear function. This one was one of the last slides of Danny, or the water retention curve. So now that we have defined the flux, we can, or Richards in his PhD, basically in 1931, put everything together, and this is how we solve in practice today the flow in soils. Okay, we just replace the flux here, and then we get the dynamics. So for that, as I mentioned, we need this to know the material properties and the constitutive relations, and we have here how it looks like an unsaturated hydraulic conductivity function, or it's a hydraulic conductivity that depending on the water content. And then here we have again our Lovett Van Genuten equation, and then the solution. Okay, in the unsaturated zone, velocity of the water is the flux divided by the water content. So if now we do the same reasoning about transport in unsaturated flows, we have to start with the same equation. In this case, the conservation of mass, variation of total concentration with time, and the flux of the solute that we have. So the total concentration, it will be the sum of the concentration in the different phases. The concentration that we have in water times the water content that we have, the concentration in gas, and the concentration that can be absorbed. In this case, I'm going to ignore these last two, and then I'm going to talk only about or we're going to consider only the concentration that we have in the liquid phase. So empirically, the flux includes two different terms, the advective term that you recognize here, and this is the dispersive term. Okay, many people put together dispersion and diffusion in the dispersive term. Well, then we can write down the advection dispersion equation that most of you already know, and we can solve this. If we have, like in every partial derivative equation, if we have the initial and the boundary conditions, we can solve this equation. Do you think that this is enough to solve solute transport in the unsaturated zone? Do you think that we will have an accurate prediction of reactions, for example, with that? Yes or not? Yeah, but that's the motivation. And I think that an image is better than 1,000 words. That was done at ETH many years ago, a classical tracer test with dye applied at the surface homothetically in the entire surface, and we can recognize that the things are much more complex than the formulation that I showed before. So, of course, many good things has been done in the last year, trying to use this formulation, the Richards and the advection dispersion equation, and modification of this with what we call the non-equilibrium models of flow and transport. And we have here a very nice summary that was done by Jirka Simonek and Van Genuten. Van Genuten was here in 2018 in this summer school, the same that we are attending now. And then they propose all of this bunch of different models, the equilibrium one, the one that I just explained, but also non-equilibrium model like mobile immobile, dual porosity, dual permeability with mobile immobile. I mean, there are many variants of this. And similar for reactive transport. One kinetic side model, but also two side, two kinetic side, dual porosity, blah, blah. Like you can increase the complexity a lot. Still, this I show only conceptually, because if I show the formulation for each of them, then we need the 2 hours for that. Just to show you conceptually these models, but this model also, and unfortunately, fail to predict accurately the reactions that take place in the unsaturated zone. Why? If we go deep into the soil, and let's focus first in the fully saturated zone, the aquifer, how it will be the transport there. Here you have this experiment in which a dye is injected from the left, moving to the right, and we see, of course, that there is a deformation in the front and there is a dispersion in the front. But if now I repeat exactly the same experiment, having bubbles of air within the system or having multiphase flow, for the same flow rate, same boundary condition, everything exactly the same, you see that it's radically different. The transport of a solute when we have another immiscible phase playing a role within the pore space. Remember, saturation, I'm going to use this in all the slides. So, now that I have motivated what will be the lecture, let's focus first in cases with unsaturated flow. We don't move the immiscible phase. And let me show you this video that we have recently produced with synchrotron images. You have the solid grains in gray color. Here you have the liquid phase. Okay, and now we remove the liquid phase and then you see the immiscible phase, the air. And now I back to put again the solids. I will remove 1/4 and we're going to inject a dye from the bottom. And this continuous injection start to show things that we're going to discuss basically in the remaining time of the lecture. Remember, there is water, we inject the dye from the bottom, but we just put a threshold to distinguish what is more or less the front. But I stop the video here because I would like that you focus you put your attention in certain regions of this image. You see this? This is behind of the front. It's still in blue color. It means that we have incomplete mixing behind of the front. We let regions behind of the front that they are not fully mixed. And they will take time to react. This is one of the responsible of the underestimation of the reaction that we have with classical formulations. So, incomplete mixing prevents classical models from predicting reactions, not only liquid-liquid, but also liquid-solid surface reactions. Okay? So, for measure of mixing, again, several definitions, many different ways has been proposed. Let me go through them very briefly because we're going to use them also later. Mixing degree, which is an indicator of the mixing that is happening in the porous medium based on the variance of concentration. Scalar dissipation rate, which is a way of how the concentration gradient depletes with time, is a measure of that. Just that we are all on the same page. This is an image in which I show concentration and concentration gradients. Concentration gradient is basically the spatial derivative of the concentration. So, then we have another indicator or measure that was introduced by Peter Kitanidis already some years ago, 30 years ago, 30 years ago, which is basically a measure of the entropy of concentration within the system. And then more recently, we are in the community using much more simpler concept like mixing volume, for example, is count the number of voxels or representative elementary volume that they have a concentration which between 0 and 1, which where we are actually having mixing between two different concentrations. Water saturation of course, first impact dispersion. And what I mean by that is that here we have two experiments with two different degrees of saturation. Here we have 30% of air, and here we have no air. And you see a front of a dye that is moving through the system, same flow rate. I don't have to convince you, you already saw the video before. They are very, very different. So if now we think about the concept of dispersion, we can compute what is the longitudinal, how is the longitudinal dispersion in this case, how spreading is our contaminant in the longitudinal direction or in the flow direction in this case, and then you see that it's radically different for the same time. But to explain the concept of dispersion or the impact of saturation on dispersion, I like to show this with particles. I think it's much more intuitive. What you see here is a simulation in the same porous medium that I showed you before. And we have particles, the color indicates the velocity, and then you see this front of particles moving more or less homothetically. Of course, there is a dispersion that is growing, especially in the longitudinal direction, or only in the longitudinal direction, because here we have a very confined system. And if now we repeat exactly the same simulation, but having some bubble of air within the system, look how different is the transport. So here plot is this, or how the sigma, the variance or the concentration increase with time. That was a nice collaboration with Thomas. And then we saw how systematically the saturation, if we decrease the saturation, we basically increase the dispersion and we go towards more anomalous transport. Please.
So in the lower one, when you were saying there's a 70% saturation, how are you distributing is it like cell-based saturation randomly distributed or?
This is an image from an experiment that we put in a numerical solver.
But when you say 70%, what does it mean?
30% of air in the pore space, 70% of water in the pore space.
So is it like taken from experiment? Where is the air, where is water?
There are the clusters that you see here, and the water is where the particles are circulating.
But you got it from an experiment, right?
Yes, this is an experimental image.
So then it's like a homogeneous medium.
Sorry?
I mean, I don't see it's a porous medium and there are grains, no?
Let's back. Yeah, what confused you is that I have removed the grains inside of the cluster of air. This is what confused you. Let's back to the previous image. No, it's a good point. If this one too moves. You see here in black color, maybe it's not the best color, but in black color you have the bubbles of air with the solid grains, and in blue color you have the water. If you want to put this in a numerical solver, I don't need the grains that are here in between the air, because the air is not moving. Okay?
So the air is not moving and you call it saturation impact. I guess you can also call it like porosity impact because you consider it as a solid phase and...
It's a good point. Yes. It has been demonstrated in 3 or 4 different manuscripts that if you consider the interface water-air sleep or no sleep, it doesn't matter too much. Why? Because the interfaces are usually protected because of the curvature, especially in hydrophilic porous medium. That's the reason behind all that. But yeah, you are right.
If porous medium changes, then here it will not change. If let's say it starts, it will move. The air, right? Because you are dissolving it. So
No, we are not dissolving anything. Here we have let's assume that the immiscible phase, in this case air or whatever other immiscible phase, it can be a hydrocarbon, is not dissolved in the liquid phase. And in this case, the flow rate is so small that viscous forces are smaller than capillary forces, and you will, with this flow rate, you cannot move the immiscible phase.
Yeah, but you can have internal recirculation on your droplet. Some fluid internal recirculation due to shear stress at the interface.
We are not moving the interface.
Yeah, it's not moving. But I mean, speaking of the no slip versus slip.
I mean, there are three manuscripts that at the PDF of velocities is almost not impacted by the, and we have done also for transport, mixing and reactions with the slip and no slip, and the difference are almost negligible. and it's because in hydrophilic the interface is somehow protected. Close to the interface, you have, because of capillarity, you have always low velocities. So at the end, if it's asleep or no sleep, it doesn't matter too much. It matters. I agree, it matters, but it's how much relevant you want to make this process. I mean, if you go for the global reaction rate in the image or in the entire experiment, the impact is minimal.
You thought it would be easy, eh?
Yeah. No, but I like this. I mean, if not, it will be boring. Lower saturation, enhanced dispersion, but this is not enough to predict reactions. Dispersion is what I mentioned before with the classical formulation advection dispersion equation. Is not enough to reproduce reaction. So, and the reason is because, of course, water saturation impact mixing. And this mixing occurs because we have a front deformation. If you see here in my images, this is, as I mentioned before, an experimental image. The front, for me, here is the line of 50% of concentration. Is here in black color. So, but the mixing zone is everything that, as I mentioned before, is not 0 concentration and is not 1. Okay, this is the mixing zone here in orange color. You can see already here how different they can be, the mixing zone between this one and this one. Basically, and then you can realize this. If we have a front that is moving like that, what is the surface for diffusive mass transfer? It's only this one. If I have a front that is like that, this is all the surface that I have for diffusive mass transfer. Okay, that's the main difference that is induced in this case by the presence of an immiscible phase. So if now we measure how this mixing volume grows in time, be careful because the time is dimensionless here. So what we can see is that at the beginning they grow both, but at the end, in the case of fully saturated condition, we reach what is expected by the theory. It's a Fickian growth of the mixing volume. This area at the end grows like T to 0.5. However, in the case of unsaturated conditions, the mixing volume grows much faster than Fickian. What is the reason behind of that? The main reason behind of that is the fact that including an immiscible phase within the pore space increase dramatically the heterogeneity in the fluid flow velocities. On the left hand side, you have the same image done before in fully saturated conditions, and then here in partially saturated condition, and you see that we create preferential path and externation zones. So how they look like the PDF of velocities for this type of systems? Again, another collaboration with Thomas. If we are in fully saturated condition, this is our PDF of velocities. But if we start to include air within the pore space, we see that we have more and more and more low velocities, but we have also, and this is for that you have here the inset, you have more and more high velocities. Okay, so we are basically broadening the distribution of velocities in our system. Just like a curiosity, we also demonstrated that in the externation zone, in the regions that are quite isolated, these kind of bubbles or that form, you can recognize here in red color a preferential path and another preferential path. The velocities here decrease exponentially. But this is just a detail. What I would like that you get from this very populated slide is that lower saturation induces more heterogeneous fluid flow velocities. So this, as I mentioned before already, can create this splitting or induce to this splitting of the system in preferential path and externation zones. So, and I thought that we were one of the first to see that, but to my surprise, of course, you are never the first. So, Pierre-Gilles Degennes is a Nobel laureate physicist, French, but conceptualized this already 40 years ago, that in unsaturated porous media, you should have what he called at that time backbone at dead ends for the transport. So Pierre-Gilles Degennes has been here many times. Actually, this is the famous paper. This is a piece of art, basically, in Journal of Fluid Mechanics. And he was here in 94, 97, most probably in 2005. 3 years ago, I was in contact with his wife, trying to find a picture or a photo of him here in Carriers. We didn't find anyone. This one is in another summer school about granular media that take, historical summer school that take place in the east coast of France, in the Atlantic coast of France. Just like a historical anecdote. So, until now we have been talking about the impact of saturation on dispersion, mixing, and we realize that behind of that, what we have is a very heterogeneous velocity field. But what are the consequences on reactive transport? And for that, I will show you, for the sake of simplicity, an experiment that we have done with magnetic resonance imaging, in which a redox reaction is coming from the bottom to the top. Here I show only 3 bits, but we have many, just that you get a spatial visualization. And the plume that you see what's going on inside of the reactive plume has been cut by a vertical plane, according to this image. I don't know if you can see from your position quite well. So, how it looks like? You will see now a reactive plume that is a redox reaction that is moving from the bottom to the top. And if we repeat, you see that is even with a very simple porous medium, you see how deformed it is, how fancy it looks like. So if we repeat exactly the same experiment but having an immiscible phase within the pore space, you will see a reactive front that is moving from in this direction. But I would like that you don't put your attention in the reactive front, which looks nice. I would like that you put your attention here. You will see some reaction that occur very late. This is what cannot be predicted by classical formulations. These reactions that occur in the back of the front. So, more definitions. So now we want to characterize what is the temporal scales of the mass of reaction product. And for that, it depends what is the model that you consider. So if we consider a dispersion diffusion from model, okay, the scaling of the mass of reaction product will be like the Fickian scaling, the expected one by the classical formulation also. More recently, other model has been proposed, like the lamella model under shear. Okay, it's basically a conceptualization that the plume or the front that is deformed is subject to a process that they call stretching. Basically, we elongate, but if you elongate something, you also compress. At the end, the area that we have here is the same as the area that we have here. And now, because you have an obstacle, you fold, then you get that, and then back again to the stretching process, and then you fold again. And I hope that you agree with me that now here we have much more surface or interfacing for diffusive mass transfer that in this situation. And this is what occurs actually in porous media. So the reaction rate has been defined or has been demonstrated that is this integral in the mixing volume of the concentration gradient times the interface length. The time derivative of the global reaction rate is basically the total mass of reaction product, and how this scale depending on the reaction. Of course, if you have a reaction, depending on the time, if you are in times that is between the advective time and the reactive time, then you have something that is scaled to T to 5/2, and if you have a time which is much longer than the advective and reactive time, it's a scale like T to 3/2. But even more, and this is something that my beloved friend Joris is working a lot now. I don't know where he is, but here it is. They have demonstrated very, very recently that this stretching can grow exponentially. And if it grows exponentially, it has been always, we have, of course, laminar flow, very low Reynolds numbers. That's no discussion about that. But we have a huge heterogeneity. Actually, chaos has been always used in the turbulent community. or it's a concept that comes from the turbulent community because they have very high Reynolds number. We don't have that, but we have a huge heterogeneity. We are able, thanks to the physical obstacles, we are able to stretch and to fold, also dramatically. And this is what they have very recently demonstrated. That this interface between the two chemicals, or between the resident solution and the injected solution with the chemical, can grow exponentially. And of course, this has dramatic implication in the reactions. So let's back to what I was talking before. Yes?
What do you mean by folding?
Folding is like, when you have a grain, you have a front that is coming and there is an obstacle, this front now will overcome this obstacle and then you are there folding the system, right?
There's no break, it's continuous?
That's a good point. So, also folding can happen not only because of you can have just velocity gradients that produce the folding. It's not only a physical obstacle. There are different ways to deform the plume. Let's put it like that. But yeah, there is Kevin is also working on that. If how continuous is behind of the grain, right? When you deform here, at a certain point you need to disconnect, right? When you overcome.
In principle, it's connected.
It's connected, right? Yeah.
In principle, you never reach if it's just advective, you never reach the critical point, right? Because you take infinite time to get there.
Yeah.
So you cannot break.
In practice, you can't
In
measure.
practice, yes.
Yeah. Run.
Wouldn't this process reduce the effect of heterogeneity on dispersion? Wouldn't this kind of kill dispersion a little bit? Say lower saturation, more heterogeneous velocity?
There is, and that was demonstrated by Amir Raouf and Majid Hassanizadet, that when you go below certain threshold of saturation, then you start to, and it's related with the correlation on velocities. So if you even use the classical formulation, when you go very low saturations, dispersivity starts to be smaller and smaller and smaller. So let's put it like that, dispersivity grows until certain threshold, but then after you start to back to the...
Because of mixing, or it's a different...
No, it's because of the velocities. It's because of the velocities within the system. If you desaturate a lot, at the end you have few pipes, few regions that control the flow, and that's all. Then you cannot disperse a lot. You see the point? You don't have too many externation zones. You have mainly preferential paths at very low saturation. Well, back to the topic. We adapted the formulation that already exists in this case for the global reaction rate, considering in this case the saturation of our system, and then with this is how it was defined in the previous slide, the stretching rate, and also the elongation, and then we demonstrate that the stretching rate can be defined like the mean velocity divided by a characteristic length. In this case, it was the pore length, and that the elongation can be defined like the mean gradient velocity, the gradient of velocity times time. So that was one of these moments that I think that it will not happen anymore in my career, because we just wrote down this simple model. We were discussing also with Tanguy Lebon, that unfortunately cannot be here this year, and the model was on the top of the experimental data. So without any fitting parameter or anything like that. I don't think that this will happen again to me. I already used my card. And what you see here are the experimental result of the global reaction rate for different saturation and different Peckless, and with samples, and then the model is with the continuous line, as I mentioned, without no fitting parameter. And then what I would like to, this model is valid before diffusion starts to be relevant. Okay? Just to clarify this point. But what I would like that you get from this reactive experiment that I just showed is that for the same Peckless, for the same flow rate, a higher reaction rate has saturation increases. It looks contradictory to what I showed before. Huh? Before I was having same flow rate, different saturation. now I have same Peglet. It means that I have to adapt my flow rate as function of the saturation to get the same fluid flow velocities. Okay? That was the discussion with Peter before in the coffee break. So, but I was very disappointed. I mean, it's important to be always disappointed because if not, you don't move. So ahead, that we were able only to exploit the beginning of the experiment. And I was always thinking, okay, how much I need to exploit all of these data that are in the longer times in my experiment. I mean, when the front even goes out of the system of the region that you can visualize with your equipment. And for that, we wanted to characterize how long it takes the reaction to extinguish. And for that, we fit a power law to the tails of all of these experimental data. And what we could see is that when we increase the flow rate, we have higher Peglets, or when we decrease the saturation, it takes longer to extinguish the reaction behind on the front. You let more incomplete mixing behind on the front, and it takes longer to extinguish the reaction. So, as mentioned, we have chaos also in the unsaturated porous media, and of course, saturation control the strength of this chaos. Let's start from the beginning. Same porous medium that I showed you before in 3D in the animation, and now we have a classical molecular diffusion, and then we have a punctual injection, and then we have our plume. Okay, this is a steady state, continuously injected dye. We can also repeat the same with a very low diffusion to be sure that advection is the main transport process. Here what I show is the interface of our plume that almost doesn't have diffusion because actually the time that it takes the tracer to go from the inlet to the outlet or the mean velocities, they are much faster than the time that you need to fill the pore by diffusion. So diffusion was negligible here. And then you see this nice Christmas tree of the interface between the contaminant and the resident solution. So we were thinking, okay, how we can characterize the process and how we can, argue that we are having chaos in porous media. That was already demonstrated by Joris and others, also by Daniel Lester theoretically before, but experimentally Joris did one of the first experiments ever. And then following the advice from them, we were saying, okay, let's cut our Christmas tree with different planes in the main flow direction, and then let's measure the interface. Okay, you see here in purple for this plane, you see here in green the intersection of this plane with the interface of the bloom that was defined in green color, and then we were measuring this length, and bingo, it was this interface length with distance from the inlet is also growing exponentially. It means that we are deforming our plume exponentially. So it means that we have chaos also within the pore space and also in unsaturated conditions. So we were doing that also having a relevant diffusion. Okay, the 10 to minus 9 meters squared per second, the classical diffusion. And then we also observed that this interface, not only the interface, also the mixing volume, at least for the characteristic length of our sample, was growing exponentially. Say, wow, it's not only advection, it's also dispersion can be also chaotic. Mixing can be also chaotic. So how to measure the strength of that? For that we were just using a exponential regression, and then we basically demonstrate that alpha in this regression for our interface, okay, was basically increasing when we were decreasing saturation in our experiment. And as I mentioned before, mixing volume for different flow rates with different samples, but also different degrees of saturation, it was growing. And what we can conclude there is that when we decrease saturation in our system, or we have a larger flow rate, we enhance the exponential growth or the exponential deformation of the plume within the pore space. Yes?
Question from both of us. How did you determine L0, like the initial length? Is it from your injection? Or
Yeah.
Directly from, but then you don't have the exponential regime right away, right?
No, it takes, yeah, but it takes very, the length that it takes, I can show you.
It doesn't grow so much during the time.
You see? And then you start to have the,
Maybe
yeah. But I mean, this distance is just few voxels.
Yeah, it's very small. Okay.
Yeah.
Thanks.
Joris.
What is the pore size in your system? Because alpha here is not dimensionless. In the
Alpha is just this exponent.
could you make it dimensionless somehow to compare with the our results?
We have done this. I see. Actually, it's in the supporting material of this manuscript.
Do you remember
Yeah.
the pore?
The pore size here is. The pore size is 200 microns and the pore throat is 30 microns.
Is it sandstone?
Yes.
So, related to that, because I was wondering, you're presenting it as a function of saturation,
Yes.
but if I have different architectures of the pore spaces,
Yes.
saturation will not mean the same thing for mixing. So how do you reconcile this? It may not be the best state variable to represent the heterogeneity that you have in the pore medium, and that's related to pore size. It seems to work fine. I'm just asking if you have thought about that.
Yeah, we thought about that. I mean,
Suppose you put layers in the medium,
Yeah.
and you create the same saturation, but
yeah.
the topology of the liquid phase. Conceptually.
I don't know if it will work. If it will be chaotic. First things, and second thing, and Joris is very aware of that. For example, here we have been able to measure and to demonstrate that we have a chaotic advection and chaotic mixing because we were having a punctual injection steady state. With the previous experiment that I showed before, in which we have a front, the deformation occurs mainly transverse to the main flow direction. And when you have a front, it's not like that. So there is, or we didn't find a way to demonstrate that it's chaotic when you have a front. Only when you have a punctual injection, that the deformation is mainly transverse to the flow direction, then you get that was your advice 3 or 4 years ago.
But you can have a gradient in both sizes. It should be the same.
I mean, I would like to go further with this and see to which extent this is, because at the end, yeah, it looks heterogeneous, but it's very simple geometry if you compare with the reality.
So, I was wondering, what did you do to measure this interface at the bottom of the rock, especially? Because when you inject, I don't know if you use X-ray or neutron, what did you use to take this image?
You can create these images with X-ray tomography.
Yeah. So when you inject at the bottom of the rock, the concentration is more spread all over the rock, and I think it's really hard to measure the interface, the length of the interface.
No, you can just threshold the concentration, and then you will get a surface.
Yeah. Okay.
And then there is a plane here which is transverse to the main flow direction, and this intersection of the plane with the Christmas tree give you all of these interfaces. Okay, and then you can measure the length of them.
What's the Becquerel number of this?
Very small. I think it's around 10 or something like that, or even smaller. Yeah. So what I wanted to finish with that is that this kind of processes or this kind of chaotic character of advection and mixing in not only in porous media but also in turbulent flow, they use this well-known Lyapunov exponent, which is just a rate of separation of infinitesimal infinitesimally close trajectories. In this case, we were having a surface, but this has been, how to say, conceptualized using a Lagrangian perception of the process, but it can be done just with the interface. I don't want to go in detail with that because are you doing a talk? No, there's no talk about that. Okay. What I want to just show you, and for me, what is more relevant here is the red and bottom take-home message is that this Lyapunov exponent, which is an indicator of this exponential growth, increase with decrease in saturation and also with flow rate. Charles.
Say a little bit about why exponential growth implies chaos.
Yeah.
What's the connection exactly?
Good point.
So it's because chaos comes from, like, the main characteristic of chaotic maps is that 2 points that are very close by diverge exponentially in time. And when 2 points diverge exponentially in time, that means that if you take a material line, it's going to explore space very efficiently.
Yeah.
The fact that the points diverge exponentially leads you to have efficient exploration of the space. The mechanism is really this stretching and folding thing. So every time you fold, you're stretching double, right? And that's what produces the exponential mechanism.
So if you think of chaos as irreproducibility,
Irreversible.
The fact that you cannot predict, you have like a temporal horizon beyond which you cannot predict anything.
Yeah. Until now I was talking about only fluid, but now let's think about how mixing control fluid-solid reaction, in this case absorption. We can think, for example, of surfactants. Surfactants are included in the chemical composition of many of our personal care products, and also, for example, in the formulation of pesticides. So most of you probably, if you have a chemical background, you know that the process of absorption is characterized by the isotherms. Okay, this is the concentration that is absorbed. This is the concentration that we have in dissolution. And this is just a very simple, this is actually the Freundlich isotherm, but isotherm can be very complex and much more complex polynomial than this one. For the sake of simplicity, let's use this one, and we're going to use Y plot here for the same KD and different beta, different exponent, how they look like the isotherm. Be careful because the units here are, like we understand, concentration, but the units for the absorbed mass is in mole per kilogram of soil. Okay? And this is how they look like. Having this in mind, we were doing an experiment in columns very recently, actually, well, 4 or 5 years ago, and then we demonstrate that if you get the KD, okay, the absorption coefficient, doing infiltration experiment for different chemicals, and doing the batch experiment. Do you know what is a batch experiment? You take vessels with different concentration, you know how much you put mass, and after 24 hours or 48 hours, whatever you decide, you measure what has been the concentration that is remaining in the liquid phase, and like that for different concentration, you know how much mass has been absorbed. This has to be at constant temperature. That's why this name, isotherm. Well, what we show is that, and we were not the first, but I think one of the first systematic studies, is that if you go to the field and then you run a tracer experiment that absorbs, or you get a contaminant that absorbs, and then you try to feed your data, you will use an absorption coefficient which is actually much smaller than the one that you determine in batch experiments. In batch experiment, you maximize the surface in contact between the contaminant and the solids. But in the reality, it's not like that. I just showed that we have incomplete mixing. Not all the solids are available for absorption. So, taking this in mind, and the general hypothesis of that is what I say, when you decrease saturation, you have less surface available for absorption. Well, we say, yeah, but what is the role of mixing? And then here we were having pulses in the same system that I showed you before. What you see here is just a zoom, okay? And then what we see here is that in the very zoomed images, that we have a halo around the grains, okay? We were forcing the absorption around the grains. So if now you have a look to this plot, this is the mass that is absorbed for different saturations versus time. And what we could see here is that the saturated case, they will not scaling anymore like Fickian, okay? Only the saturated case at the end, because you mix Fickian, you absorb Fickian. But the other one, no, the other one, they will lose in strength. And the reason I was thinking, the hypothesis was, okay, mixing here is, mixing in the unsaturated condition should be playing a role. Well, for that, we say, okay, remember the isotherm. The isotherm is in one axis, the concentration in dissolution, and in the other axis, the concentration that is absorbed. How is the concentration in dissolution changing time? And for that, we were measuring the mean concentration, the dilution that we were having in our system. And then when you have a look here, actually, the unsaturated cases, which are the darker colors, at longer time, they start to dilute. The mean concentration within the system was decreasing faster. It's because I'm mixing faster. While in the case of saturated conditions, be careful because the block is lock-lock. It's a huge difference. It was decreasing much slower. And of course, if you dilute, it means that you decrease the concentration that you have in dissolution, then you decrease your capacity of absorption. So we were doing that also for different betas, and we observed also how beta, the exponent in the isotherm, was controlling the absorption. The shape is the same. The beta basically control only the magnitude, but the decrease with saturation is not linear. And the reason because the decrease with saturation is not linear is the fact, and this is probably the most important figure for this assertion, is the fact that when you decrease saturation, the relative area of the liquid-solid interface decreases linear. Okay? But the fraction of the porous medium that is behaving like a stagnation zone or like a preferential path, it doesn't decrease linear. And this is the control behind of this non-linear hash function of saturation. All good until now? Multiphase flow. Now let's take the spoon and accelerate the mixing. Think like that. Think that you have your coffee, you have your milk, and the spoon will be the bubbles moving within the pore space. If you move faster your spoon, you mix faster the coffee with the milk. This is basically what we're going to see with the bubbles now. Before, some definitions that Danny partially introduced before. We have, first I would like to describe how the immiscible displacement in porous media take place. And for that, there are different dimensionless numbers. Danny already introduced the capillary number, viscous forces versus capillary forces. If capillary forces are more important than viscous forces, you don't move the immiscible phase. But if it's the other way around, then you move the immiscible phase. We can think about also the viscosity contrast between both phases is very important. And then the bond number is the one that relates the capillary forces with the gravitational forces. The people in Norway, the group in Norway has been working a lot on this bond number. So there is another piece of art from Leonard Mant in 1988 in Journal of Fluid Mechanics that proposed this phase diagram, okay, in which we can have, if we plot the log of capillary number versus the log of viscosity contrast, we can have an stable displacement. If we go to this region, we can have a viscous fingering, okay, and if we go here in this region, we can have capillary fingering, also call it invasion percolation. Having this in mind, let's move now to see how this multiphase flow control mixing, reaction, and also reaction with the solid. So, what is the dispersion during the transient displacement? And this is a nice experiment from Danny. He shared with me a few days ago this image. You have seen this in his presentation. He was injecting water or a dye that was diluted in water in pulses, and then you see here that the soil, that in this case is a volcanic material. You have here dry condition and here you have wet conditions. But what is very visible there is the instabilities that we have in the front. Okay? Very recently, there is this paper at pore scale in which they have the saturated case, the stable invasion, and also the unstable invasion. And they study the dispersion that these different type of injections introduce in a pulse of contaminant. So I think it's quite obvious that when you move to a more unstable invasion, similar to the one that Danny did several years ago in the field, the dispersion that you get of this pulse of contaminant or chemical increase dramatically. But that's if we think in a transient displacement, if we have a system that is in this case dry and then we re-wet. But now I would like to show you how it will be if we have a system that already include two immiscible phases, how this will control the mixing process. And this is a very common problem. There are many soils that are polluted by hydrocarbons. The hydrocarbon here can be the black color, the water is the blue color, and now I'm going to inject a solvent because I decided that will be my remediation method. If I inject a solvent, you see what's going to happen. And I will let the video running. You see how the solvent, the distribution of the solvent was mainly controlled by the movement of the water. The solvent doesn't mix with the water. They are not good friends. And then you see how the solvent is diffusing in the hydrocarbon. Well, if now I repeat exactly the same experiment but having a lot of statistics, like in this microfluidic experiment, we can repeat the experiment having only the hydrocarbon and then we inject the solvent, and at the end, if we use this mixing degree like an indicator, and at the end I will fully clean my system, I inject solvent, at the end all the hydrocarbon goes out of the system. But if we have water here in blue color that is there, like is what happened in soils, actually we got a surprise because for very similar initial condition we can have very different evolution of the mixing degree of how we mix our solvent with the hydrocarbon. And the reason behind of that, and Danny will kill me now, the reason behind of that is because the water can reorganize in different ways. Okay, because of capillary forces, viscous forces, etc. Even if you have a very similar initial condition in terms of saturation, and statistically you have the phase is distributed equally everywhere, you can have very different results. What we were doing we were doing an upscaling. We say, okay, let's define a representative elementary volume in our images, and then like that we define the saturation of water, okay, that we have in our system. With these fields of saturation, we were using geostatistics. We compute the variogram and the correlation of the variogram, and then we demonstrate that the system in which the water organized in a more heterogeneous way, it was the system actually that helps to mix more. Something that we have already seen before with the unsaturated conditions. So, more heterogeneous the water organized in the pore space, more mixing we can have of our solvent to remediate, for example, a soil.
Did you say same initial condition also
of saturation in both experiments was the upscaling, the two images of saturation was extremely similar. statistically speaking. We have, of course, more experiments. And then some of them, because it's a very random process, some of them evolve towards something very more heterogeneous, some others evolve towards something that is not that heterogeneous.
Dynamic effect of the.
Yeah. And that was controlling the mixing of the solvent with the hydrocarbon. Also, is many times used the co-injection of two phases to remediate a polluted soil. It's not new what I'm talking about. So, how it will be a stationary two-phase flow, injecting both liquid and gas simultaneously in a soil, how this will control the chemical reaction. What you have here in this video is in black color the liquid, in white color the gas. And I'm going to inject both simultaneously. Okay, I'm injecting both. A certain rate of flow rates, okay? And then you see this imbibition drainage that occur.
Is this a fraction of the gas and the liquid are fixed, or what do you mean?
The two flow rates, they are fixed, and they are
the flow rate of the gas
and of the liquid. Okay. Yeah. And they are injected simultaneously. This is a method that is used, for example, for remediation. And then we were thinking, yeah, but I mean, how this control mixing and reactions? Let me show you a chemiluminescent experiment in which we have fully saturated conditions. And then you see this reaction front moving from the left to the right. Okay, there is a resident solution. We inject another chemical, and this chemical react with the resident solution, and then you get this pulse of light, because actually it's literally light, that is moving through the pore space. If now I keep the same flow rate for the liquid, and I start to inject the immiscible phase, you will see there is no need to do quantification how different is the reactivity in the system. The volume of the liquid is injected, or the flow rate is exactly the same, but the reactivity of the system changed dramatically. Remember what I said before with the spoon and the coffee. If now I have a spoon moving very fast, I will mix quickly the coffee with the milk. Here the bubbles are my spoon. We don't see them because of the experimental limitations, but the bubbles are moving there at the same time that we are injecting the reactants. And then the bubbles are enhancing the reactivity in the system dramatically. If now we plot this for the different conditions, we have single phase flow experiment, and this is the intensity that was captured by the camera. And if now we repeat exactly the same experiment with the same flow rate that in the single phase, but we inject a bit of air, a bit more of air, a bit more of air, then you start to see that how the reactivity in the system increased dramatically. And then, of course, at the end, the reaction extinguished. It's not infinite. Well, what is behind of that? Behind of that, my hypothesis was, okay, there are fluctuations of saturation within the system. If you see at low flow rate for gas, we were having this oscillation of saturation in my domain. If we increase the flow rate of gas, we increase the frequency of oscillation in saturation. And if we go higher, even higher. So then, at that point, I say, I'm pretty sure that there should be a correlation between the fluctuation of saturation and the peaks of the reaction. And this is what I showed you before, okay, the peaks. And then here we have the saturation. We did many experiments, and we see that the period of reaction fluctuations, so these peaks, the period of these peaks, okay, and the half period of the saturation fluctuation, it means that we have an increase and a decrease, increase, decrease, increase, decrease. The half period of that, they correlate perfectly. So it's the changes in saturation, basically one of the main drivers, or the fluctuation in saturation, one of the main drivers of the reactivity within the system.
No question. What we see here, it's what happened at the outlet of your domain, or it's a laboratory?
It's the saturation computed in the entire image.
Why don't you use a correlation instead of period matching? If you were to correlate them, you'll see.
I know, actually, here, we did a a Fourier analysis to get the period of the peaks and also to get the period of the fluctuation of saturation.
But if you didn't have periodicity, you could use just correlation.
Yes. Yeah, you can do by correlation. You can just go with the peaks and.
Could you imagine an experiment where you have no saturation fluctuation but still a bubble that are moving? And like this experiment would have the same increase in reaction rate. So
probably yes.
Saturation fluctuation is the real variable or the relevant?
I mean, it's multiphase flow. That's
it's more the motion of clusters that drive the reaction rather than the saturation.
Why we have a fluctuation of saturation is because of the size of the domain. I think that if you have a huge domain,
you don't see any.
You don't see fluctuation of saturation.
So it might be better to quantify maybe fluctuation in velocity or in.
Yeah.
Do you think that the frequency of the saturation fluctuations depends on the size of the domain too, or just the magnitude?
No, also the frequency probably depends on the size of the domain. Yeah. So what we did, of course, is to compute the total mass of reaction product that we produce, and then we realized that, of course, when we increase the velocity of the spoon, when we increase the flow rate of the gas phase, we were enhancing the production of mass. And then we were, for all of our experiments, we were trying to see what they follow in terms of mass of reaction products versus time, with all the models that I showed you before, the diffusive one, the one of the lamella basin model, the exponential, these are the two for the lamella basin model, these are the exponential one, and some of the experiments, they show also a chaotic behavior. So it means that the bubbles, they also enhance or induce an stretching, exponential stretching of the front. How multiphase flow control now the fluid-solid reaction? And in this case, I'm going to show you only dissolution. Here I don't show you the liquid phase. This is the gas phase in yellow color, and then you see the liquid phase that is pushing the bubbles with these vectors. So let's use this very well-known system, which is the calcite system, okay, in which if you dissolve CO2 in water, you get carbonic, the pH decrease, and then you can dissolve, and if you move in the other direction, basically what you produce is precipitation. I show you here, if we have a wall of calcite, this is the molecule of calcite with this size, actually, 4×10⁻⁴ micrometer, and then we have the carbonic acid that is moving close to the wall of calcite. This can be advected, but can also diffuse, and dissolve the walls. So for that, we were using these kind of micromodels that we call geomaterial microfluidics. We were using limestone. Actually, you can recognize it in the fossils. There are some alveolines here. And why this very weird shape? I wanted to, because this experiment of dissolution, they take forever. So I wanted to get a lot of information with very few experiments, basically, which is the dream of all of us. So then we create channels that they have different width but same depth, and we were having two dead ends, one that was in the flow direction and another one that is in the shadow of the flow. So with this geometry and with the chemical model that I showed you before, then we show that if we have only water with a bit of CO2, no bubbles, then we were having this dissolution. You already realize that most of the dissolution occur in one channel. But if we have multiphase flow, you see that the dissolution was much more homogeneous all over the micromodel. Okay, why that? The reason behind of that is that when you have multiphase flow together with dissolution, bubbles, basically because of capillarity, like Danny mentioned before, alternate between channels. So the bubbles, if the medium is water wet and the bubbles are non-water wet, then the bubbles will go to the larger pore. So then you dissolve, you create a larger pore, the bubbles go there. Now most of the liquid goes to another channel. When the other channel is larger, the bubbles will go to the other channel. And then like that you alternate bubbles between channels, and this at the end homogenize the dissolution. And this is what I wanted to show you. You have here for the multiphase flow at the beginning, you have that. This is the bubbles moving through the system. Be careful because the water is transparent. And then at later times, the bubbles, they are mainly moving by this channel, but during the duration of the experiment, they were also mainly circulating here, and then after circulating another channel, they were alternating. We also, of course, get the velocities of the liquid phase, and you can already realize here that, of course, the velocities when you go to the dead ends, they are very, very small. But it's difficult to see what I want to explain you in this image, but you will get in the next one. If now I have the velocities in my system in 3D, if now I go very close to the walls, at the point that the diffusion is much shorter than the advection, diffusion is the main process, then we can compute close to the walls what is the Peclet and what is the dun color. What do you see in these images? What is the difference between this one, for example, and this one in terms of Peclet? If you see, this image has much more homogeneous Peclet, and we have demonstrated this statistically, than this one. This one has a Peclet which is in one channel which is completely different than the rest of the channels. So the dissolution, and also if you go to the dun color, is even more evident. You see dun color here is for single phase. Dun color is completely different in this channel where you mainly have the dissolution than in the rest of the channel. While if you go to a multi-phase flow system, dun color is more or less the same everywhere.
What kind of dun color are you talking now? Is it the diffusion one or the...
It's the diffusive. No, it's the advective, sorry.
But then the giant dun color in the dead ends is just because there's no flow.
No, here it's just because there is no flow.
So
Yeah.
with diffusion we have the...
Yeah. Do I have 10 more minutes to show how this matters in reality, in the real life? So, with this I conclude what is the control of multiphase flow on fluid-solid reactions. And very, very briefly, and I will go quickly, how the interplay of flow, solute transport with all of these mixing process and reactions, and microbial life, how they interplay in reality. I think that all of us, we believe that the underground is full of life. This is an image of a microbial colony in a root. So just to motivate. We can have, if we think in microbiology, mainly bacteria, we can have different state of life. There we can have free floating or planktonic state. Okay, bacteria are navigating in the liquid, but we can have also a sessile form of life, which is actually what we call biofilm. And then I really like this image because the author, they show clearly that the hydrodynamics of core control this formation of the colonies, but also the fact that the colonies, they are not impermeable. The flow can go through the colonies. When we are in the first free floating stage, we can have also microbial behavior like motility and chemotaxis. Motility is the navigation of the bacteria because they have a flagellum, and then there are different patterns that has been described. I don't want to go very in detail with that. And chemotaxis is when the bacteria, like we're going to do in 20 minutes, sense the food and then go towards the food. So, but this is what has been described in free flow. If we go to a confined system like porous media, motility can be altered. Because in porous media we have well-connected pores, but we have also dead ends. And this creates what is called hopping and trapped. In the hopping phase, we here see for Escherichia coli many consecutive positions. What you can see is that the velocity of the bacterium increased dramatically. When we go to a dead end and the bacteria doesn't know how to find the door, then the velocity or the mean velocity decreases substantially. And also the angle, this is the angle of rotation. Okay? Of course, when I don't find the exit, I rotate a lot looking for the exit. Why all of this? Why all of this is because in soils and in the unsaturated zone, we find actually, we have already demonstrated very heterogeneous chemical landscapes, and also because of very heterogeneous velocity